All right, continuing on with our acid base lecture right here. We mentioned that this problem was a little bit more involved, so let's go ahead and take a little peek at it and see what we got here. All right, so here you have two different acids, both of them strong, hydrobromic acid and nitric acid. They both have different concentrations, and you are adding different volumes of each one. And then you want to figure out what the pH of the solution is. So that is somewhat involved. But remember, if you know the volume and the molarity, you can convert that into what is almost always the goal, the mole. Because if you can get to moles, then you can sort of take these variables out of the equation. The fact that this one you had a large volume with a little weaker concentration, this one's smaller with a little stronger concentration. A lot of factors come into play there, but if you can get it into moles, then we're counting actual H pluses, and that is the nitty-gritty of what we're looking for to do pH. So start by doing this. Just take remember, you got to convert that into liters. So 0.5000 liters, and we will use the molarity as a conversion factor, moles per liter, to give you your number of moles. 2 sig figs because of that. And then you can add and figure out and do the same conversion for the nitric acid, and now we know we're comparing apples to apples here. And essentially, once we have moles, we can just add those up. Those will be nice 3 places to the right with both of those. We can add that up and then do the total volume. The total volume. So that you might remember this one from an equilibrium problem that we did. You got to remember that it's not 500 and it's not 250, but it's going to be 750 milliliters total. So, and that of course needs to stay in liters so you can get moles per liter, which is ultimately what we wanted, of course, is the concentration of the hydronium ion or hydrogen ion, which is 0.17. So then we go and say, well, if I know the concentration of H3O+, I can just plug that into my old equation. pH equals negative log of the hydrogen ion concentration. You plug in the number, and notice that's 2 places to the right. For the pH we'll have 2 places to the right because our concentration had 2 sig figs. Okay, so we know when we do our pH, we'll go 2 places to the right. And in this case, 2 sig figs either way. So, but it's always place value 0.77 is the pH of this solution. And these things should always kind of make sense. You got 2 relatively strong acids that you're putting together in a not that much volume. You do that in a large beaker. So that's going to make sense that the pH would be very low because it's a very strong acid. All right, now some of you might have been thinking, when we introduced this unit, we said water, which we have in this reaction, can auto-ionize and make more hydrogen ions. And the question was addressing here the pH of the solution. We got these extra hydrogen ions that came from water. Well, there's 2 things about this. Number 1 times 10 to the minus 7th is a very, very small concentration of hydrogen ions. And when you have a strong acid, you're going to be adding this H+. That will cause this auto-ionization of water, according to Le Chatelier, to shift to the left, making even more water and less hydrogen ions. So in other words, it was really, really small, and it got a lot smaller because of the acid that we're adding. So that's why you can leave that out of the mix and don't have to worry about the auto-ionization in most of these problems. So if there's a pH, is there something called a pOH? You better believe it, because that's the opposite. Auto-ionization made OH ions too, so we can do the negative log of base 10 of the hydroxide ion concentrations and figure out the pH, pOH. So you got something like this. We know that Kw, and we know that the OH concentration is the same as the hydrogen, so pOH is also 7.0 in a neutral solution. So again, that's at 25 degrees Celsius. We can know not only what the concentration, and again, they keep leaving that M out of there. Don't put that M in there, just because it's a concentration value. And pH, of course, doesn't have units. So again, this is 7.0, a nice neutral solution, which is, of course, the same as the pH. All right. Now, a review of strong bases. That was our great 8. Just remember CBS, calcium, barium, and strontium. They're farther down. Those are the 3 that are toward the bottom of family 2, and then all the group 1 cations except for francium, which doesn't even really exist. So so you've got those 8 that you will need to recognize. So you see, and that's why it's up to you to look at KOH and say, oh, that's a strong base. So basically, you're going to have 1.5 molar concentration of OH, because it's all going to break up and leans completely to the right because it's a strong base. So our equation, pOH equals negative log of the OH minus concentration. All you got to do is plug that in and run that on your calculator, and you will see that turns out to be a positive number when you do log of 1.5, and so you got to leave that negative sign on there. So this is the pOH scale is off the scale, and this would be a deadly poison. A 1.5 molar KOH solution would destroy most organic life. That's just strong drain cleaner is what we're talking about there. Okay, so this is 2 sig figs, so 2 places to the right when you're doing that. Now, here's something it's a good conclusion to make here. So if we know Kw equals 1 times 10 to the minus 14th, that Kw. So if you just do negative log of everything, then basically you can get, if this was pure water, you'd have 7 plus 7 equals 14, which of course is a true statement. But that will work in these solutions that are at 25 degrees Celsius. So if you know the pH in these systems, you can say that they're going to add up to be 14 because the pKw is 14, and that's a kind of an easier way of doing that when you think of these as with the P in front. Now this number is 10 to the 14th. It's actually a numerical value, so it's not really a measurement. So you don't have to worry about significant figures, and that allows you to do quick calculations. If you know one, you can figure out the other in terms of pH and pOH. So let's go ahead and look at this. the pH of a 3.5 molar sodium hydroxide solution is going to have complete dissociation. So therefore, complete dissociation. So that would give us pH equals the negative log of the hydroxide ion concentration, which is negative log of 3.5. And then again, real strong base solution, so not surprisingly, it's a negative 0.54. So the thing is, they asked for the pH. All right, we can do the pOH directly using the concentration of this, and now we can apply that newfound little trick I just showed you, that the pH plus the pOH equals 14. So if you want to find the pH, you take 14 minus a negative 0.54, and the pH of that solution would be 14.54. That looks like sig figs are kind of all over the place, but if you know your rules, 14 doesn't count, that's a number. So you're really using 2 sig figs on this one. So that's what you need in your pH is 2 sig figs, and 14.54 has 2 significant figures because place value, 2 to the right. So 14.54 is the correct answer for that calculation. All right. So that's going to be very useful for you on the worksheet that you're going to be doing with this. Here's a little bit of the Chatelier's principle again in terms of the thermodynamics of it. This auto dissociation of water is endothermic. So the heat is over here on this side. So if you increase the temperature, remember you add here, it's going to drive it to the right, and you'll get more dissociation occurring. Okay, so that's just an application, and of course this is just saying if you were to cool the substance, it's going to come back to the left. Remember, you leave a space, it'll fill the space. So you have to know that this is an endothermic reaction, and that would answer some questions about how would temperature change the pH of water. And these would be real minimal changes, but they do exist, and it can be an important part of a problem, is that the temperature can change the autoionization of water. Okay? All right, so now we are done with 8.1 and 8.2, and we can just read the daily instructions for what to do for the problems. Take care.